Good evening, everyone. Have you ever wondered about the strange and fascinating world of quantum physics? Today, we're going to dive into the mysteries of this mind-bending field and uncover what you might not know about quantum physics. Quantum physics, the science of the very small, governs the behavior of particles at the atomic and subatomic levels. It's a realm where the rules of classical physics no longer apply, and the universe behaves in ways that defy our everyday experiences. Our story begins in the early 20th century when physicists were trying to understand the nature of light. Classical physics, which had brilliantly explained the motion of planets and the mechanics of everyday objects, fell short in explaining the peculiar behavior of light and atoms. Enter Max Planck, a German physicist, who proposed in 1900 that energy is not continuous but comes in discrete packets called quanta. This radical idea laid the foundation for quantum theory. Planck's hypothesis arose from his work on blackbody radiation, where classical theories failed to explain the observed spectrum of emitted radiation. This notion of quantized energy revolutionized our understanding of the microscopic world. Fast forward a few years and we meet Albert Einstein, who in 1905 used Planck's quantum hypothesis to explain the photoelectric effect how light can knock electrons off a metal surface. This was one of the first concrete pieces of evidence that light can behave both as a wave and as a particle, a duality that lies at the heart of quantum mechanics. Einstein's explanation showed that light consists of particles called photons, each carrying a quantum of energy proportional to its frequency. This particle nature of light challenged the prevailing wave theory and earned Einstein the Nobel Prize in Physics in 1921. But it wasn't just light that exhibited this strange duality. In 1924, Louis de Broglie, a French physicist, suggested that particles of matter, such as electrons, could also exhibit wave-like properties. His hypothesis was soon confirmed experimentally, leading to the realization that all matter has both particle and wave characteristics. De Broglie's groundbreaking idea extended the concept of wave-particle duality to all forms of matter, suggesting that every particle has an associated wavelength inversely proportional to its momentum. This wave nature of matter was confirmed by electron diffraction experiments, which showed that electrons could produce interference patterns similar to those produced by light waves.
This wave-particle duality was encapsulated in the famous Schrödinger equation, formulated by Austrian physicist Erwin Schrödinger in 1926. This equation describes how the quantum state of a physical system changes over time. One of its most famous implications is the concept of a superposition, where particles can exist in multiple states simultaneously until they are observed. Schrödinger's equation provides a mathematical framework for predicting the probabilities of different outcomes of quantum measurements. It introduced the concept of the wave function, a mathematical description of the quantum state that encodes all the information about a system. And this brings us to one of the most famous thought experiments in quantum physics, Schrödinger's cat. Imagine a cat placed in a sealed box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the atom decays, the Geiger counter triggers the hammer to break the vial, releasing the poison and killing the cat. According to quantum mechanics, until the box is open and the cat is observed, it can be considered both alive and dead simultaneously. This paradox highlights the peculiar nature of quantum superposition and the role of the observer in the quantum world. Schrödinger devised this thought experiment to illustrate the absurdity of applying quantum superposition to macroscopic objects and to challenge the interpretation of quantum mechanics. Quantum entanglement is another mind-boggling phenomenon. When two particles become entangled, their states become linked, so that the state of one particle instantaneously affects the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, has been experimentally verified and is being harnessed in emerging technologies like quantum computing and quantum cryptography. Entanglement suggests that particles can share information instantaneously, defying the classical notion of locality, which states that objects can only be influenced by their immediate surroundings. This non-locality of entanglement has profound implications for our understanding of space and time. Speaking of quantum computing, this is one of the most exciting frontiers in modern science. Traditional computers use bits, which are either 0 or 1. Quantum computers, however, use quantum bits or qubits, which can be both 0 and 1 at the same time, thanks to superposition. This allows quantum computers to perform certain calculations exponentially faster than classical computers, potentially revolutionizing fields like cryptography, materials science, and drug discovery. Quantum computers leverage the principles of superposition and entanglement to solve complex problems that are intractable for classical computers. For example, they can factor large numbers efficiently, which has significant implications for encryption and data security.
Quantum physics also challenges our understanding of reality itself. The famous double-slit experiment, where particles such as electrons create an interference pattern like waves when not observed, but behave like particles when observed, suggests that the act of measurement affects the outcome. This has led to various interpretations of quantum mechanics, including the Copenhagen interpretation, which posits that physical systems do not have definite properties until they are measured, and the many worlds interpretation, which suggests that every possible outcome of a quantum measurement actually occurs in a vast multiverse of parallel realities. The double-slit experiment demonstrates the fundamental role of observation in determining the behavior of quantum systems, challenging the classical notion of an objective reality independent of measurement. In the realm of everyday technology, quantum mechanics is already at work. It underpins the functioning of lasers, transistors, and MRI machines. Our understanding of chemical reactions and molecular structures also relies heavily on quantum principles, making modern chemistry and material science deeply rooted in quantum theory. Lasers operate based on the principle of stimulated emission, a quantum process where photons induce the emission of identical photons, creating a coherent beam of light. Transistors, the building blocks of modern electronics, rely on quantum tunneling, where electrons can pass through energy barriers that would be insurmountable according to classical physics. Yet, despite its successes, quantum physics remains deeply mysterious and often counterintuitive. It challenges our classical notions of determinism, locality, and reality itself. Physicists are still grappling with its implications and seeking a deeper understanding that might one day lead to a unified theory of everything, bridging the gap between quantum mechanics and general relativity, Einstein's theory of gravity. One of the major goals of modern physics is to develop a theory of quantum gravity that can describe the behavior of spacetime at the smallest scales, potentially revealing a more fundamental layer of reality. One of the most tantalizing aspects of quantum physics is its potential to unveil new aspects of the universe. For instance, quantum field theory, which combines quantum mechanics with special relativity, has led to the development of the Standard Model of particle physics, a theory that describes the fundamental particles and forces of nature. However, the Standard Model is incomplete, as it does not incorporate gravity and leaves many questions unanswered, such as the nature of dark matter and dark energy, which constitute the majority of the universe's mass and energy. Moreover, quantum physics has implications for our understanding of information and computation. Quantum information theory explores the fundamental limits of information processing and communication, leading to the development of quantum algorithms that can solve problems more efficiently than classical algorithms. Quantum cryptography, which uses the principles of quantum mechanics to secure communication, promises unbreakable encryption based on the laws of physics. Quantum mechanics also intersects with cosmology, the study of the universe's origin and evolution. The early universe, immediately after the Big Bang, was a hot, dense state where quantum effects played a crucial role. Understanding quantum fluctuations in this era is essential for explaining the large-scale structure of the universe, such as the distribution of galaxies and the formation of cosmic microwave background radiation. Quantum cosmology aims to apply quantum principles to the entire universe, potentially leading to new insights into its birth and fate. The philosophical implications of quantum physics are profound, prompting debates about the nature of reality, causality, and free will. The observer effect, where the act of measurement influences the outcome, raises questions about the role of consciousness in shaping reality. Some interpretations suggest that the universe is fundamentally probabilistic, challenging the deterministic view of classical physics and suggesting that uncertainty is an intrinsic feature of nature. In conclusion, quantum physics is not just about complex equations and abstract concepts. It's a window into the fundamental workings of the universe, revealing a reality that is far stranger and more wondrous than our everyday experiences suggest. As we continue to explore the quantum realm, we are likely to uncover even more astonishing phenomena that will deepen our understanding of the universe and our place within it. Whether it's through technological advancements, philosophical insights, or new scientific discoveries, the journey into the quantum world promises to be one of the most exciting adventures of the 21st century and beyond.